Hi, my name is Seon Joo from Yonsei University. And the title that I have here, Hybrid AI Neurosymbolic Inference System to AI, isn't really the title of my specific talk, but it's rather the title of the whole project that we're doing. So this whole Korea AI Summit is run by this big government grant called AI Innovative Hub. There are about 12 teams in this project, and our team, a group of 10 professors, have been working on this neurosymbolic inference system to AI. And the goal of our project was to try to develop system to AI through neurosymbolic inference. And one thing I would like to say is that we wrote this grant in 2020. So that's before ChatGPT. So whatever we said in back in 2020 that, like this transformer, blah, blah, blah. So you kind of also, this was time when there was this big debate between the connectionist versus the symbolicist. So we are basically saying, oh, well, we want to play somewhere in between, trying to connect the symbolic AI with deep learning. But I guess OpenAI has proved that, well, we probably don't need symbolic AI. Just put a lot of data in it, and it would generalize to anything, right? But anyways, I still do believe that the symbolic AI has its place in AI. And what we've been working with was there were two basically, well, this is still saying that deep learning has challenges in understanding causal relationship. And the specific data domain that we are looking at were the videos. So here, this is still about the project itself. We've been trying to develop algorithms in absence of ground truth data. We wanted to build user interactive models and also real-time decision-making systems, all before ChatGPT. Right? So the first research topic that I would like to talk about is on object-centric learning and how we can manipulate these objects through image augmentation. And this is under review. And here's the motivation for this. So the binding problem is a fundamental problem in computer vision, I would say, rather than computer science. So it's a fundamental problem in computer science. And what we are trying to do is, given an image with unstructured input, we basically want to do segregation, or we could also call this as a segmentation. So given this image, we would like to know where the objects are and how we can represent each object rather than images itself, and then also understand the composition of those objects given an image. So this is called the binding problem. And there are three things that we need to cover in the binding problem. One is the segmentation. Second is the representation. And lastly, the decomposition. The first problem that we solved was the segregation problem. And I talked about this last year. So how do you decompose an image in a self-supervised way? So this is called the object-centric learning. It started somewhere around 2020. And the basic mechanism that people use to do object-centric learning is to use slot attention. So basically what they do is, given an image like this, you basically need to come up with a soft segmentation map of each object. And then for each object, you come up also with the representation with some sort of vectors. Right? So every time I try to kind of explain object-centric learning, a lot of questions that I get is, why are you even doing this? There's just so many good segmentation algorithms, like SAM. Why are you doing this? Could you just use one of those segmentation methods? And it's a little bit different when you run image segmentation or video segmentation. What you do is you're doing supervised learning. You are working with ground truth labels of those segmentation, but with this object-centric learning, you're doing this unsupervised. You don't have any labels about the objects or the segmentation maps of those objects. So given just objects, you just need to figure out where the objects are and also how you can represent those objects in images. And basically, as I said, the main mechanism will be the slot attention. It's the plain attention algorithm. The only thing that is a little bit different would be that the attention is applied to the channel axis rather than your spatial axis. So basically what you have is you have some initialized slots, a set of vectors, and then during this slot attention algorithm, basically all these slots would be competing with each other to basically claim their position of each pixels. So for example, so these are, there are 4 slots here, and each slots are basically saying, well, this pixel belongs to me, that pixel belongs to you, and so on. So after several iterations of this attention, you can see that the first slot basically is attached to this object in the scene. The second slot would be the background. Third and fourth objects are basically represented by slot number 3 and slot number 4. Right? So that has been the slot attention. Last year at CVPR, we presented this work called the slash, which basically we basically introduced more stable algorithm for the slot attention with better segmentation map. So that was last year. And then this year we wanted to solve the other 2 problems, representation and also composition. So if we can achieve this stable segmentation, what can you do with this thing? Because now you have all these diffusion processes where you can basically say something and they can create images. So what can you do with the object-centric learning? Basically, we wanted to kind of all solve the problem of representation as well as composition. So here's more specific goal here. Basically, through slot attention, we have set of vectors that we call slots that basically represent the objects in the images. Then what we can do is we can start to manipulate these slots so that we can move the position of those objects, change the colors or the positions of those objects using human's instruction, right? So this is kind of like how we would edit images. The mechanism is a little bit different, right? We basically edit the properties of objects by manipulating the slot representation that we got from our previous work. So how do we do this? Remember that we still don't have any ground truth labels here. So this is all basically unsupervised, or you can call this as a self-supervision. We solve this through image augmentation. So given an image, we can always kind of change the position and color and the size with this data. So we basically translate the location of objects. We can also manipulate the colors of the objects. We can also change the size of those objects. So easily we can kind of augment more images with different object properties. And basically what we do is, this is the original slot attention. So after doing slot attention per object, we have their representation. And then we basically add another layer. This is a very small MLP that will basically modify the representation of the objects based on the instruction given here. An instruction here would be a list of instructions for object positions, colors, and their size. So given those objects, we are going to change the representation that would basically kind of change some things, some properties of the objects here. And when we train them, we can basically add a loss where the changes in the objects with this slot update should be equal to the augmented images that we made ourselves. So this is pure self-supervised learning. So with this is a little bit more detail about our architecture. I'm kind of gonna skip this. So we are still using our original slot attention, but we are going to update the slot update model with the image augmentation. So this is the result. So this is the initial object. This is the initial image, and here are different instructions. And as you can see, we can manipulate the image on the object level pretty well if it's about the positions, colors, or the size of the images. Another dataset, Tetris dataset, we can also change the shape, not the shape, the position, color, and the size of those little blocks in this data set. One problem with this slot attention algorithm is that it only really works on data that looks like this, mostly very simple data or synthetic data. If we kind of try to extend this to real images, it doesn't work so well because we are trying to do image segmentation in an unsupervised way. So there is a little bit of a gap over there. And why is this result good? Because everyone can think, well, can you just use GPTs or any of those stable diffusion models to do this? So here's the input image. And if we ask these stable diffusion models to say, I'll make all the objects color yellow, here are all the results from the stable diffusion. It doesn't do it, right? And then this is our result. And if we ask GPT to do something about this input image, for example, move the pink metal cube to the bottom left corner, it gives you this weird answer. Scatter object to the edges except for the center one. You can see this is what we actually want, and it just creates a whole new thing, right? So there's still a gap here, like the stable diffusion models or any of those diffusion models are great, but I don't think they're actually doing anything on the object level. They're basically working with the representation for the whole image. Not on the object level. So somewhere out there, I think there's still a place where you can work on getting a better representation of the objects. Another thing that I'm kind of considering here is, well, everyone uses transformer as the backbone, the diffusion models or the tokenization process, right? For languages, I think current tokenization works fairly well for images or maybe even for videos. If you think about how we actually make tokens from images and videos, I'm not so sure if it's the right way. Basically, we divide images or videos into multiple patches, and each patch will be transformed into a token. So I guess what I'm trying to get at is if you can somehow make this work in real scenarios, this could actually become a very natural tokenizer, right? In an unsupervised way, you know where the objects are, you have the representation of each object, and those representation naturally becomes the token that a transformer-based models can use. Right? Here's some more results on the object level manipulation. I think there's still a place, although many people may think that this seems to be too old, right? With all these diffusions and the large language models. I think, especially from the representation point of view or tokenization, there are several things that we can work on in the future. And one thing is we're doing this without any ground truth labels, but there are a lot of data set that provide segmentation maps, right? So why not use them? That's been my question to my students. You know, we do have some data. So if we use those labels to learn better representation for the objects, why not do it, right? And then, of course, we want to go into a more weak supervised setting. How can we adopt diffusion models into this OCL framework? And also, how can you incorporate these techniques into videos would be a very interesting direction. So that's one of the topics that I wanted to talk about today. And another thing I want to talk about is the videos. This is also a recent submission from my lab. We're calling this as open-ended hierarchical streaming video understanding with vision language models. And one direction for video understanding that my group has been proposing was online streaming video understanding. So computer vision community has been working on video for several decades. And if you think about traditional video understanding tests, you have video recognition. So you basically have a set of frames that represent an action, and your AI model has to recognize what kind of action is in that sequence. That's totally offline. Someone has to basically, from a video, cut the start and the end of an action, and then provide that into the model. So it's not really useful for real-time scenarios. So a lot of video tasks that people work on is basically in the offline process. You're assuming that you have the whole video, right? So at a frames perspective, you have access to past frames, but also future frames, right? But in real life, for us, we're basically getting real streams of videos, robots, like it's online, real-time streaming videos. So all the video systems, we're claiming that needs to be an online process, that it only has access to current and its past frames, not the future frames, and also it has to work in real time. And another thing with video understanding in terms of action recognition is that the labels in the data sets it doesn't have the hierarchy of an action. So for example, the labels would be either like cooking, right? But what does it mean to say an action includes in cooking? But inside cooking, you have preparing something, you have stirring something, boiling water. There's a lot of sub-actions within this label of actions. So you need to be able to understand actions, but at the same time, with its sub-actions as well. It's kind of like when you try to understand the language, you understand a sentence by understanding the words in the sentence. After understanding the sentence, you can understand the paragraph and so on. So that also applies to actions. So here we are, I think I can show you a video here. So basically how our kind of algorithm works. Hopefully I have the right codec. Okay, so basically our input is a streaming video, the one frame by one frame. And we have a very small RNN-based model called the streaming model. And what it does is, given a frame, it basically detects whether there is an action start. From that, we can also estimate the progress of an action, and also we can detect if this is an end of an action. Why is it so slow? Okay. So with all the frames using the streaming model, we can detect. Come on, why is it so slow? I guess I'll have to just move this manually. So streaming model says this is an action start. Oh, here's an action start. You can see the progress of an action. If it's an action start, we'll save the frame into a context memory. And then the frames will keep coming in. And when the stream model says this is an end of an action, then we also put that frame into the context memory. And when there's an end signal, then we'll basically call a VLM, be it GPT or any other VLM, to basically kind of recognize what the action is. And the VLM will basically say loosen the bolt, and then same process on and on. So basically what this does is not only we are just detecting a sub-actions, we kind of rely on the generalization capacity of the VLMs to recognize the hierarchical actions in a video. For some reason, the video really doesn't work so well here. To move the sliders myself. So here's, you can see that at some point, it has detected an action. It's a sub-action or a sub-step, and it basically says, stirring the pasta and cooking meatballs. So we can do this, and at some point, we can basically also say, as a whole, this video is preparing a pasta dish with sorted vegetables, with steps and subsets. And this is basically happening online real time. Okay? And you could think about using a very large VLMs to do this test, but it will basically be very expensive. Because like it has to like basically process every frame every time, and you have to call the VLMs. But what we are doing is we are basically using a very cheap RNN, and using this RNN basically to learn when to call the VLM. So basically, we are only calling VLM when it's time to basically put it into languages to say what it's doing. Okay, so I think that's it for me, and if you have any questions, I'll be glad to answer them. Thank you.
Okay, thank you for the great talk. I have a specific question on the second topic. So you call VLM, right? So is the VLM takes video as an input, or it takes just separate individual frames as an input?
So it would basically have a sequence of images, right? When we call VLM, can you switch? 요거 슬라이드로 좀 바꿔주시겠어요? Okay, so here, in this context memory, what we have is frame information of a video sequence that this streaming model says start to the end. So it would have several frames that contains the initial frame to the last frame, and that would be maybe 5 to 10 frames, and we are using that to call VLM.
So my question is, so the VLM process the video, or
only it's really on the images level.
I see.
Yeah, okay. Because now even for all these ChatGPTs, like if you ask ChatGPT, can you process videos? It will basically answer, Well, we don't do it directly. They only do it in an indirect way by giving a sequence of images, not videos. So in a similar way, we are basically giving a sequence of images.
Okay, makes sense.
Okay.
Thanks.
Any more questions? Okay, so thank you, Professor Kim, for your talk. So yeah, that concludes for this session.